Hi, good morning. Welcome back to this lecture series on flipped classroom, a lecture dialogue 2 on PN Junction diode. I am Akhilandeshwari, faculty, Indian Institute of Information Technology, Tiruchirappalli, along with my team members, Ms. M. Anita and Ms. G. Chansirani. In the previous lecture, we have discussed about the introduction to PN Junction diode. We have discussed in detail about p-type and n-type material. We have discussed about how a p-type material is formed, how an n-type material is formed, what is meant by this PN junction, how it is formed, and what happens when you place a PN junction in the equilibrium. Now, in this lecture, we will discuss in detail about what is meant by this diode, what is meant by this PN junction as a diode, and what is biasing of PN junction, types of biasing, and VI characteristics of PN junction diode. Now let us see what is meant by this term diode. This term diode is derived from Greek, which means di means two and ode means node or terminals. So basically diode means two terminal devices. Now how PN junction can be formed as a diode, a PN junction diode. Now we will take two terminals from PN junction, so one from the P side and another from the N side using the metal contacts. So the terminal from the P side is called as an anode, while the side or the terminal from the N side is called as a cathode. So we have a two terminal PN junction diode with the nodes or terminals as cathode and anode. Anode that is connected to P side and cathode that is connected to the N side. Now let us see what is meant by this term biasing. Right. So biasing is basically nothing but giving some external voltage. You are supposed to give some external voltage to your device. That external voltage can be through some battery or through some power supply. So you are going to give some supply to your device, and this biasing or based upon what terminal of battery you are connecting to your device, based on that you can classify biasing as in two types. So one is the forward bias and another one is the reverse bias. In the figure that is shown here, your diode, two terminals are taken from it using a metal contact. You could see that, and we call that as an ohmic contact because it has zero resistance, so that no loss occurs because of this terminal. Now this figure shows it is an forward biased PN junction diode. Now let us see what is meant by this forward biased. Right. When I give a P side of the diode to the positive of the battery and N side of the diode to the negative of the battery or the power supply, we call that as an forward biased diode. It is simple, positive to the P terminal and negative to the N terminal. Okay, now what happens when you forward bias this PN junction? Think for a while, pause your video and write down your answer in your course journal. Once you have written the answer, you can play the video. Okay, now let us see what happens when you forward bias this PN junction. Now we have connected the positive of the battery to the P side of your material, diode or PN junction diode. Now as you know, the same charges will repel each other. So we have connected positive, and hole is also a positive charge carrier. So they will repel from the terminal side and they will try to go across it. So they will try to cross the junction and reach the other terminal. So similarly, we have connected the negative of the battery to the N type of the PN junction. Now similarly, the electrons will try to move or try to cross the junction and move towards the other terminal. But you know, there is an brick of walls, that is, we have immobile ions. They will stop the flow of electrons. This is in the case when your battery or your power supply voltage is less. Now when you're going to increase your voltage, the power supply, now what happens is across the junction a high electric field is formed. Now this makes, or this gives the potential to your electrons and holes to cross the junction. So when we increase this external voltage, the electrons from the N side and the holes from the P side will cross the junction, and this will constitute a current in the device, right? So in the previous slide, you could see I've marked a current direction I, that is from positive. So this is because I denote, or we usually denote, the conventional current direction. So conventional current direction is from positive to the negative, right? Okay, so when we increase the voltage, the electrons and holes cross the junction and we constitute and it constitute the current actually. Now what happens to the depletion region? Pause your video, write your answers in the course journal. Right, now when your charge carriers crosses the junction, the depletion layer width will reduce, because you know, depletion region is nothing but it is depleted of free electrons or free holes. Generally we can say it is depleted of charge carriers. Now when the charge carriers are crossing, then obviously it means the depletion layer width is decreased, right? And the external voltage after which the charge carriers start to flow across the device is called as a cut-in voltage or the knee voltage. And usually it is 0.7 volt for silicon and 0.3 volt for germanium. This is theoretical, and when we do the experiment practically, we could find the range of cut-in voltage is 0.5 to 0.6 for silicon and 0.2 for germanium. Now let us see what happens when we reverse bias the PN junction. Pause your video and write what is mean by, or what can be the reverse biasing of PN junction. What terminal should be connected to cathode and anode. Pause your video. Okay, now let us see what is mean by this reverse bias. Okay, so in this figure you should get a clear idea about reverse bias PN junction. So I have connected the negative of the battery to the P type material and positive of the battery to the N type material, right? So we have reversed the polarity when compared to the previous biasing type. We have now just reversed the polarity. We have connected negative of the battery to the P side and positive to the N side. Okay, now what happens actually? You know, opposite charges will start to attract each other. Now I have connected the negative of the battery to the P side and positive of the battery to the N side. So the electrons will move away from the junction and they start towards the terminals. So similarly, the holes will try to move away from the junction and they start moving towards the terminal, the negative terminal of the battery. Now what happens to the depletion region? So obviously the charge carriers are moving away from the junction. So we could say the depletion region width will be increased when you reverse bias it. Okay, now I'm just going to increase the reverse bias voltage, similar to the case of forward bias voltage. Now what happens when I increase this reverse bias voltage? You know, the P type material, the majority charge carriers or holes and obviously we will have the minority charge carriers as an electrons. Similarly, for the n-type material, we'll have the majority charge carriers as an electrons and the minority charge carriers as the holes. Now these minority charge carriers, that is electrons from an p side and holes from the n side, they will try to cross this depletion region. Of course, they are minority charge carriers, so the movement of this minority charge carrier will constitute a current, of course a small current, and we call that current as the reverse saturation current. Okay, now let us see the VI characteristics, or the voltage ampere characteristics of this PN junction diode. Okay, so in this figure you could see two graphs. One is in the one is in the second quadrant, and another one in the fourth quadrant. So the second quadrant, or that is on the right hand side, it is nothing but your forward bias characteristics of an PN junction diode, right? Okay, this is forward bias characteristics. It is marked as an VD. VD is nothing but the bias voltage, ID is nothing but the diode current, and in the forward bias characteristics you could see initially the current is 0 until some voltage, and when that particular voltage is reached, the current starts to increase rapidly, right? So that point is nothing but our cut-in voltage or knee voltage, which is nothing but the barrier potential to overcome the barrier, the immobile barrier. So when we give a forward bias voltage and that voltage is less than typically 0.7 for silicon, then no current flows, no charge carriers crosses the junction. So you could observe a zero current in the device, across the device. And when we increase our external voltage beyond that cut-in voltage, so typically 0.7 for a silicon or 0.3 for germanium, the current started to increase, and it increase rapidly and it reaches this saturation. Now in the third quadrant we'll come to this reverse bias. So in the reverse bias, when you just give a reverse bias, a small current, initially it is 0, a small current will flow across the device. That is because of the movement of minority charge carriers. So this current, the reverse saturation current, would be in the range of microamps. It flows, and when you increase this voltage, reverse bias voltage, after some volt, that is, say for example, we call that as a breakdown voltage. Now what happens is the diode will break down and the current will flow rapidly. You could see a sharp increase in the reverse bias characteristics. So that point we called as a breakdown potential, or a breakdown point, in which in the reverse bias diode, after some particular voltage, the current start to flow rapidly. So that point we called as a breakdown potential. So some diodes can be operated in the breakdown potential, but we need to be very careful in it, or otherwise in sometimes it can damage the device itself, right? So as a summary, so this VI characteristics, so the first quadrant is the forward bias characteristics and the third quadrant is the reverse bias characteristics. Now let us see how the diode current equation can be constituted. So I'm just going to tell you the expression from just observing the previous graph, right? So the diode current ID is nothing but it's proportional to the reverse saturation current and the diode voltage into eta Vt minus 1. So the term eta is missing here. It is showing as an a rectangular box, it is nothing but eta. Now Vd is nothing but the biasing voltage, Vt is nothing but the thermal voltage. As we all know, PN junction is a semiconductor, and semiconductor will depend upon the temperature, right? So it has the temperature dependency, and even we could say the forward bias and reverse bias characteristics, or the resistance of forward bias and reverse bias diode will vary with respect to the temperature. For example, the reverse biased diode, when you increase the temperature, the current, the reverse saturation current gets increased, right? Okay, so this Vt, the thermal voltage, is nothing but Kt by Q, and K is Boltzmann's constant, T is temperature in Kelvin, and Q is charge, 1.6 into 10 to the power minus 19. And Vt, you can always have this approximated value when we solve the numerical problems in the next class, I mean in the in-class activity. So this Vt is 26 millivolt for the room temperature, that is 300 degree Kelvin. And eta, as I told you, eta, it is now denoted as a rectangular box. So this eta is nothing but the emission coefficient of the diode. That is nothing but how this diode we have fabricated it or constructed it, right? Either the PN junction is just updraft, or it is we are used a step index or a graded index. Depending upon that process, this emission coefficient will vary. And as a general, we say eta is equal to 2 for silicon and 1 for germanium, or to be precise, we call the eta is equal to 2 for low currents silicon diodes, and eta is equal to 1 for the high current diodes. That is how much of current that is flowing through your diode will determine the eta, right? So generally, as I told you, the reverse saturation current will be in microamps and the diode current will be in milliamps. All right. So as a summary, in this lecture we have discussed about what is mean by the term diode, from where it is coined, how a PN junction can be used as a diode, what is mean by biasing, what are the two types of biasing, what happens when you bias, forward bias or reverse bias your PN junction diode. Then we discussed the VI characteristics and this diode current equation. Answer the question, that is quiz question, that is followed by this lecture, and state any two applications of this PN junction diode in any real time application, like where it can be used. You just think it of because this diode, when you forward bias, more current is flowing, so I said it is in milliamps, and when you reverse bias, it is having in microamps. So you can say the diode will allow the current flow in one direction. So where this can be practically useful, so think on it and post your discussion in the discussion forum. All right, so in the class we'll have think, pair and share activity followed by this or based upon this discussion, right? Okay, thanks for listening to this video. Have a great day.